Today we'll be looking at stability analysis. Okay, we have seen that the explicit method, okay, we cannot take the delta t value to be whatever we want. But in the implicit method, you can give this subscript. We know that we can give a larger time step in the implicit method compared to the explicit method, and we have seen that if we increase the delta t for the explicit method, after some value we were getting the solver was blowing up, or it was giving us not a number. Okay, the scheme was getting destabilized, and we will see why. Okay, so we are going to do stability analysis for a given equation and for a given scheme. So every scheme in CFD and every method, like implicit method, explicit method, or semi-implicit method, they have to be first analyzed using stability analysis. Unless we prove the scheme is stable, and we have to prove that the scheme is stable under certain limitations, and we have to use the scheme only in those limitations. Okay, to do that, what we are going to consider is the unsteady heat diffusion equation, again one-dimensional heat diffusion equation, and we are going to discretize it in time and space. So what do we get? We are going to use forward difference in time followed by second order central difference in space, that is T I plus 1 minus 2 Ti plus Ti minus 1, all at nth time step. So we'll just look at why the explicit scheme would not work properly when we do this. Okay. Now let's say that let A denote the analytical solution of the partial differential equation. Okay, let A denote the exact solution or the analytical solution of this equation. Let's say we have it prior. Let D denote the exact solution or this exact solution of the difference equation. Okay, what is the difference equation? Equation number 2. Okay, this is the difference equation. I already told you that as delta t tends to 0 and delta x tends to 0, this equation will tend to the original equation, but these two are not mathematically equivalent. Okay, so A is the analytical solution and D is the exact solution. Now let's also denote N, which gives the numerical solution of the simulation. Okay, so what happens is when I code this difference equation and I run it, I get some solution, and I am denoting this solution with N. What is the difference between this difference equation and the one that we code? The major difference is that in a computer, what happens is you cannot store a number beyond certain digits. For example, if you have a 32-bit system, okay, 32-bit based architecture, you have 64-bit architecture computers these days. So what happens is it is going to allocate only 64 bits for a given integer or float number. So what is happening here is in a computer, say the value of pi 3.14159 is only denoted to till some digits. For example, say 32 digits or 64 digits. Okay. So what is happening here is we are not getting the full representation of this number. Even a number like 1.0 is denoted by 0.9999999 in a computer. up to say 8 decimals or 16 decimals, depending on your setup, depending on your code. But it's not going to go up till infinity and represent this 1.0. That's why you get the solution that you get from the difference equation is not the same as what you get it using a code. So we can represent these errors, rounding off errors. Okay, we already know that there is a rounding off error in computer, right? That's what I'm talking about. We can say that this numerical solution is nothing but whatever exact solution that you get out of the difference equation plus some error. Okay, this is nothing but rounding off error. Okay, now we know that this numerical solution satisfies this difference equation. Okay, this is what we are trying to compute using a code. So what do we get? If I substitute n here, I'll retain the same indices. Okay, I'll retain the same indices. Say n is some solution that I get at each and every point and each and every time step. So what do I get? If I substitute this here for each and every point, I get n plus 1 I minus n I by delta t, okay, equals to alpha by delta x square n I plus 1 minus 2 n I plus n I minus 1. Now we can substitute d plus e instead of n. So what do I get? I get d n plus 1 I plus e n plus I minus d I n plus epsilon I n over delta t is equal to alpha by delta x square d plus epsilon n I plus 1 I plus 1 minus twice d n I plus epsilon I plus d n I minus 1 plus epsilon n I minus